record. Yeah, everything's good. Okay, let's go ahead and a little bit recap that what we had been doing yesterday. That can you remember we were talking about this data set. See, this is the data set that we were talking about. See, it's called see studentmat.csv data. See, so they are all the description. This one, yeah. See, this is the detail of that all the 33 that variables. See, school, gender, age, address, family size, parents, status, mother's education, father's education, mother's job, reason for selecting that particular school, guardian, travel time, study time, failures, and school sub. See, that's the educational school sub. School educational, that extra educational support coming from the school, family support, paid activities, nursery, higher, whether they want to take the higher education or not, internet, whether they have the internet facility or not, are they in a romantic relationship or not. This is a key part that we're going to try to, with the aid of this one, we are trying to explain this one the mainly. That's the whole discussion that throughout this whole assignment. And I think one thing I missed. I want to open that homework as well. Let me see. That is open. Hold on, give me 1 second. This okay. Assignments, homework 4. Yeah, homework 4. I got that one too. Okay, not that one. And family relationship, the free time, see, going out, see, alcohol consumption per day, alcohol consumption per week, health, absence, the number of assessments, and then the grades for 1, 2, 3 classes. It's a final grade. These two are second period grade like that. So we have this data. What we did was we imported data here. This one. Oh. So then we have some libraries over here. Then first question, introduce your purpose and scope. Create a story of the DGP that might be responsible for the variation in that absences. Why the absences are varied? Because we thought because of that kind of a relationship, that's the major thing that we took into account. There might be other reasons too, other factors going to affect the absences, but at the primary stage, we're going to take only this one. If you find a relationship like that, this can be explained by this another variable. As we did in the chapter 7, can you remember you have a y, whatever the variable to be explained, that's called the dependent variable, should be on y-axis, while the independent variable can take the values arbitrarily, independently. That's why we're going to call that one independent variable or explanatory variable. And in this case, that in this primary stage, we're going to pick like an explanatory variable, categorical explanatory variable being selected. Okay, so we have a y here, x-axis has like another variable as well. So those two will be putting into that this kind of like a equation in this form, absences equals relationship. You cannot say without this one. This is the key part in statistics. That's why statistics, if you put only these two, that's called the deterministic. That relationship is deterministic. That means number of absences can completely that explained by a relationship on like a straight line, like in mathematics. This is mathematics. It's mathematics. If you add the error, that's statistics. That's how the mathematics differ from statistics. And this is the real picture. This is a very abstract picture. The people built a formula based on the abstract, that intuitively they built up something abstractly, theoretically. That's not going to work when it comes to the practical application. You have to have other parts. See, unseen parts should be added to that one to explain the whole thing. That's what the people did from time to time. See, in the beginning, they had only this one only. Not only. They were thinking that they can be explained that y with the x only. That's what we learn in mathematics. But later on, they added. People thought, no, there should be some kind of a variation in this kind of a relationship. That variation not going to be same for point to point. It's going to differ from point to point. That variation should be tackled, addressed, and how? By adding an error term to that one. That error has to be minimized at the end of the day. How could we going to minimize? By trying to get the sum of squared error or mean squared error by taking minimum. Or if it cannot be minimized that one at this primary stage, what are you going to do? You're going to add another variable, second variable. You're going to square this one. Sometimes you might going to square this one and see whether what's going to happen. Instead of going to like a relationship only, you square, you get a cube. You can do so many things, or you're going to transform this one to another variable and then bring it back and then put it into the formula. That kind of a various aspects we're going to talk throughout your whole career in this masters down the road. Very nicely that everything laid out piece by piece, we're going to add. At the end of the day, you have a vast knowledge for that you can easily address any kind of issues. So that's what we are planning to see. At the primary stage, we simply pick a one. Or you're going to pick two variables, three variables, and their interaction, then relationship plus family support or something. Get together and then add to here and then see how it's going to work. Or later on, those two, family support and the relationship, those two, that for instance, I'm talking about, for instance, that one that if these two interact to another third variable, put that third variable at the same time, if you put another variable here, that variable, what's going to happen? Secretly, it's going to go and have a relationship between this one as well as both. Same time. This is called the confounding. You're going to see those kind of stuff down the road. Not only this guy, let's say family support, that variable supposed to have a relationship or association between with this guy only, absences, but it will affect this one too. Those are called the confounders. See, this relationship will be confounded by this relation. I'm not talking about this one. Let's say if I have the fam sub, okay, like this. That's what I'm talking about. Okay, this guy, see, this guy gonna go ahead and have some kind of built up some association with this one while he's having this one. It's called this relationship has been confounded by this relationship. So those kind of things, if it is confounded, what are you going to do? You're going to take it out or put it back. Or sometimes this is going to be something called the third variable become interactor. It's called the effect modifier. Effect modifier means like they're going to try to build up the interaction between those two, something like this. Let's say that if I go ahead and add here. They built up an interaction. See, that means they get their like that. Come another term. Okay, so these two plus other stuff. See, third variable. That's then in that way this become an effect modifier or interactor. These all are controllers. These all are controllers. Those are called the control. You're trying to primarily this guy we call the outcome. This is we normally call the exposure. That's why we use the word exposure. That's the primary one. Primarily, you are trying to find the relationship between these one. The rest of them, that will be added to the model called the controllers. Those controls, are this a controller count confound or an effect modifier? Those kind of a discussion you build up later on. But in the primary stage, what we're going to do, we simply go with the simplest one. But don't get misled by that one thinking that this is the only way that we can do things. No, this is a primary stage. You don't build up that much of knowledge. Okay, so you are trying to lay down a foundation only. So this is, so they're going to look into this one. See, especially that you're going to talk about those kind of things in the analytics 625, 620 down the road. One course for the continuous variable being added here, the other variable the same way. Other course, we're going to talk about when that this variable becomes a categorical variable, the way that we have over here. See, exactly the way that we have over here, not with one, by adding more variables to that one, being all the variables categorical, plus this one also categorical. But here, remember, at this primary stage, this one is always quantitative, numeric, okay? Numeric. And this one categorical. In next class, in the first thing we're going to do, we're going to make this one quantitative as well. And we're going to talk about that's called regression. So then we built up this one, describe the research question, give the rationale for studying that kind of a relationship between the between romantic relationship and the absences. See? You are trying to build up some kind of association between the romantic relationship and the absences. What do you think the romantic relationship would be? Explain the variation in absences. So we discussed about that one thing. Discuss this one, then we went to the word equation. Word equation. Absences equals a relationship means a romantic. That's the way that how that being given in our original data set. Romantic relationship has been given in romantic by the name of romantic other stuff. That's the error. See, then the romantic has only 0 and 1, no ears, categorical explanatory variables. See? This one absence is quantitative response variable, and categorical explanatory. Oh, I would like to use the word exposure. That's the word that we heavily utilize in biomedical research, exposure, the major one. The main variable is called the exposure. As I mentioned earlier, the other variables will be added later on. Those variables are not exposures. Those are called controllers. Mainly you are about thinking that absences will be can be explained by romantic. As I explained earlier, the rest will be added. Still, you can add more variables, but you don't add many variables for the sake of adding. No, we cannot do like that, because then we're gonna just the elegance of that equations go away. You have to keep the elegance of the equation, and then to come up with the like exact solution or the best solution. There are no something called best solution, but at least the better solution at the end of the day. In order to do that one, you cannot throw that many variables. We have a 33 variables. You might be thinking all 33 variables, we're going to explain the number of absences. Sorry, except for these two, that 13 more. No, you cannot, because that's why if you throw, you have to make sure you're going to take them out to come to a very stabilized, very representative model at the end of the day. How could you going to do that one? You can do that one like a forward selection, backward elimination, stepwise, those kind of procedures we utilize later. Okay. Then here that we hear that what are the frequencies of the categorical demographic variables. See, demographic variables, you can talk about the gender, address, school. See. So you can go to see gender, address is the categorical, address, school, those are all categorical. No? Those are all categorical. Here we are. Looking into the structure here too. See, you can see that how many variables are characters, integers of the categorical, and integers meaning numeric. Okay, mainly. So this one we talk about this one. Oops. Okay. Install the package. Okay. Let's unmask that one. Okay, that's good. See, it's a proportion number of that females and males in this category. See, and family. See. Address. See, urban and rural. No, can you remember the addresses are not the real addresses. Addresses mean the location, the demographic location in which that they will live in. Because mainly any countries, that areas can be divided into 4 parts. No, urban, peri-urban, rural, and deep rural. Any country can divide it into 4 parts. Normally, that's how they do that. Scientists do that: urban, peri-urban, rural, and deep rural. But here they go with only 2, urban and rural. See? urban and peri-urban together, rural and deep rural has been then absorbed into rural. So then that one, sorry, we already did that one. Then the school, see, they have two types of school they were attending to. Those are the two schools they have included in this particular. But I have to mention you something. By just picking only two schools, we cannot just generalize something at the end of the day. That's why these researchers are very heavy. Somebody going to give to you data to be analyzed. With that data, how could, if they not been taken across the certain regions, so the countries or the district, cities like that, those are called the nested design that you cannot come to a conclusion. That's why that when we analyze the data at the end of the day, it's not simply just take the data and analyze and give it back to your client or your boss. You have to make sure those data being picked. Like let's say that something you want to come to a conclusion based on a certain district. That district one you cannot generalize to that all the districts unless otherwise that it's been all the data being selected and then samples are taken in a proper manner in which those all the samples are representative sample to represent pretty much all the districts or all the states like that. Otherwise you have to go that, let's say that you want to talk about a certain school, then school is within a county, county is within a district, district within a state, state within a country, like that. Those are called the nested design, hierarchical. So you have to go to that kind of a design, hierarchical design, nested design. So many things involved. That's why you have to learn pretty much everything. That's why you cannot stop at even masters. You have to go even PhD and then go beyond that one to complete your knowledge at the end of the day, because otherwise you are missing a lot. Okay, so then they will say, what are the 5-number summary? There's a, we know how to find the 5-number summary. See, that's for the age, you can go get that one, or that simply you can see summary. So pretty much same thing. Provide the descriptive status of your outcome and explanatory. Outcome variable is nothing, but if you want to go that one, you can go to the favorite statistics. Descriptive statistics means like this is the statistics. That means mean, median, mode in sample are called the descriptive statistics. Okay, descriptive statistics. See? But when it comes to the, excuse me, when it comes to what? Categorical variable, you cannot go with the favorite stat because we don't have a number. You have to use tally. That will tell you only romantic, whether how many students in romantic relationship and how many students not in romantic relationships. And see, or you can put both together by that. And then you can find the favorite statistics of the absence of biromantic relationships. See? Yes, no, see the breakdown. You can take those breakdown. And then we create the histograms. Okay, you can use that if you have a like the fancy way adding that so many things. Okay, even the ggplot2, that the package, you can use that one. And then see, that's the one that we are using over here. That, but see, there's something very nice. See? I'm sorry, rather than using this one, you can even use the GG formula one too. It doesn't matter, but this one gonna give you nice. Okay. Even by looking at the favorite statistics, 5-number summary, you can get a clear idea here. See, look at the favorite statistics. Go to the absences 0 and Q1 median. See, median is the middle, like that's a fulcrum on which that seesaw has been placed, and in that way that it's like a seesaw, the data. It's a fulcrum. See, median going to divide this one into 2 parts, in which that lower portion is going to have the same number of data points as the upper portion of the distribution. See? That will divide that into that equal weights. Those are weights actually. See? That means number 50%, 50% median. Mean is not that one. Mean is the center of the data value. If you go to the mean is based on the data value. Median is based on the rank of the data value. Rank, okay. The mode is the highest one. See, the mode. See, mode is here. See? So the mode and median. See, mode and So median here, sorry, mode is like a see, almost here. And Q3 mean, see, mean 5.7 somewhere here. The median, after median, you're gonna see that one, mode, median, mean, right skew. If you want, you can take this out. If you feel like this is unnecessary thing to be explain everything, you can take them out. You know the procedures how to take them out. Right skewed, okay. Create histogram. That one, provide a visualization of the research question, reference the figure in your report. What do you see? See? Some graphical representation should be that added to that. See, this is our problem. The absences by romantics. See, we had that discussion yesterday. Yes, no. See. Okay. By looking at this one, they are quartiles. See, pretty much. Look at me. They have outliers too. See, they'll have outliers less than the outliers of sometimes they don't have that many outliers, but here many outliers. See, unusually, even though they don't have a romantic relationship, they were absent from the school for other reasons. Other reasons. Those reasons were not discussed over here. That's why this visualization is very important. Later on, you systematically add the other thing. So they consume alcohol or not, the family support, as I mentioned earlier. Anything you can add to this one and see how it's going to go. That's why I'm telling you, when it comes to the research very rigorous. Okay, you have to go with the reality. Doesn't matter whether it's like something issues that we can discuss or not. You have to, because sometimes some biomedical researchers that you cannot include a certain fraction of the subjects, that because of the legality, then some people, researchers, going to move on to somewhere that different jurisdiction and then pick the subjects. So those so many things involved, because at the end of the day, that's the sciences to be done in a certain way, because it's not going to have like a crossing with the, like a legal system. They go parallel, legal system, religion, and then this our sciences. They don't mix up any time. They go parallel to each other. So when it comes to the researchers, they were heavy. Sometimes they're gonna take into account everything and then discuss. Okay. So we can have here, see, this is the maximum. Okay, this is the maximum. These are outliers. The whisker gonna stop over here. You know that the whisker is nothing but the thing, upper whisker. This is the one upper inner fence. Upper inner fence. Upper inner fence. They both don't have a thing. Look at no whiskers. What prompted us not to have a whiskers over there? See? Can you remember lower whisker? I don't see that one. See, it's gonna start from Q1. What's the reason? Q1 is nothing but 0. See? Then see, Q1 is 0. Q1 is 0 as well as minimum 0. There's no gap between. So minimum gonna be on the bottom of the box. See, minimum here, minimum also here, as well as the Q1. So that's why you don't see a whisker here. There's no way that whisker. If you have a whisker, that gap between the Q1 to that minimum is how much? 1.5 IQR. That gap. This gap, which is called the height of the box, if you multiply by 1.5, that's the height, that's the length of the whisker. Here the same thing. What's the length of the whisker? 1.5 IQR times C. That's that part. So you're gonna add that one to this one to see that lower bound. See. So you have a Q3 here. Q3 to you're going to add what? 1.5 times IQR. That means this is the 1 times IQR. So here at the end of the day, you're going to have what? Upper inner fence. Anything above that one are outliers, except for this guy, last guy. Even though it is outside this, within that range. Even as I mentioned that earlier, you can categorize this one based on not only simply outliers. You can think about like an inner fence, middle fence, outer fence. See, So the inner fence to middle fence, we're going to call the mild outliers. Inner fence to outer fence, we're going to call heavy outliers. Outer beyond anything beyond outer fence, we're going to call the highly risky outliers. If you want, you can categorize like that. And based on that one, then later on you come back and say, hey, we're going to keep our mild outliers over here. So you can keep the mild outliers, but you have to bring the discuss that one. You have to mention that one and say, hey, we have a 3 types of outliers. Based on that one, I prefer to keep the mild outliers for that in order to come up with the best solution at the end of the day. That kind of a broader discussion should be built up by mentioning this one. Without mentioning this one, the audience or the client or the reader, they have no clue about what we're talking about. Everything should be very explicitly expressed rather than implicitly telling, because you are given a report. In the report, everything should be very clear cut and the query should be clean. So if you mention those things, then they will realize rather than they simply that go with this one. So we mentioned that one. Okay. So the same, pretty much same story over here. Okay. We can talk about that one. See here that we can go for a, see this kind of a histogram. This is a what? Stack histogram. See? Comparison and contrast you can do. And then faceted histogram. So many things you can draw and then show them visualization to the comparison and contrast. Very easy that you rather than that so much thing being already within this graphs. So when you throw this one on like that, your presentation or any that try to explain to your clients, they can see it clearly. Then you can a little bit explain to them. See, there are outliers here. See. If you want, you can get rid of that. You can get rid of that one and then consider on this part. See, so nicely that we have one peak here, one peak, right skewed, but this, see, the mode, see, very high, and low. See, we can discuss it. See, later on, you're going to write the research question. Absence, see, absence is explained by the romantic. Your research question, you're going to put in that one. See, this one. See, in word format. Absences, mean absences for this one. Sorry, empty model. We're going to go to the empty model. If you go to the empty model, you have a mean absences plus error, or B naught plus error, or Y bar plus error, intercept plus error, B naught plus E, B naught plus error, again E with I. Empty model, we can check with the empty model. See, that's the B naught. That's the average number of absences based on regardless taken into whether female or not. Nothing has been taken into account. Without accounting anything, if you go ahead and look at the average of the number of absences, that should be around 6 days. On average, 6 days. Whether that being affected by some other variable, that's the one that we are trying to build up over here one by one. See, here go now one, then you go to the summary, we talk about this one. We talk about this one in large scale yesterday. I told that this one, okay? I discussed this one. Why you have only one estimate? That's the same thing that you see over here. Same thing, 5.709. It's going to appear again. See, look at the error. Look at the here. 5.709. If you go to the error, first quartile, the minimum is negative 5.709. If you go ahead and check the errors for each and every data points, eventually those errors we can be even that range from the minimum to the maximum errors I'm talking about. And can you draw like a histogram for the errors and get the smooth curve? What would be at the center? Where's the mean of error? Minimum we have first quartile, median, third quartile, max. The minimum of error, not the error square, is always 0. You know that, okay? It's always 0. See, 0. Look at your third quartile. Look at your minimum. Look at your median. Median is, see, whether this is going to be right skewed or left skewed. See, median is close to this one. See, close to minimum than close to maximum. That means what? Right skew. It's right skew, but that's the tricky part here. It's right skew. Look at that here. See, if you go ahead and check this error, if you take into account error, I'm gonna little bit draw by hand and show to you. Okay. You mean that? Okay. I get the numbers. Okay. First I get the numbers. So that median is negative 1.79. I'm sorry, negative 1.709. 709 and minimum is negative 5.709 and your maximum. I'm mainly focusing on maximum. Max is 69.291. 91. This is error. Look at this one. The minimum is 5.709. See? If you go to the mean, this is the mode. This mean is the mean. Mean should be 0. This is what? It's a median. Or second quartile. Quartile 2. Look at the maximum. It should be right skew. But in this class, or any that statistical that data analytics or the data scientific that research, you're gonna think this one is what? Well shaped, not right skew, not any skew. See? So instead of that one, they're gonna for their mathematical tractability and easiness. Mathematical tractability and easiness, what they're gonna do, they're gonna think this one, okay? They're gonna think this one, you see, something like that. See? Bell shape, see? See? Bell shape and symmetry. Normal curve distribution. They're gonna think like that, having mean at the center. See, this one we do what for mathematical tractability and easiness. You cannot apply the other theories and then get messed up. Yeah, because of that, you go with that one. Bell-shaped distribution. Normal law, we can call this one Gaussian. Gaussian distribution. That's been named after Carl Gauss. He's considered to be the father of mathematics. He's a big boss. There's nobody above him. So, see, even though he's in mathematics, he put that hand in everywhere, in physics too. Gaussian flux, Gaussian distribution, mathematics and everywhere. See, he's a genius because of that. See, look at me. So this is the one we're going to take into account. We know mean is this one, that's not enough, but we saw that in this picture, it's been shifted to this one. That's the error. I say error. Okay. So everything we do that, that's why but if you need the exact solution like that, go with this guy, you do the adjustment, you do the transformation. That transformation you're going to learn down the road. If you really want to, down the road, you want to do your research in master's, PhD, or postdoc, or research paper when you become a faculty or working at a company. There are research wings in companies. That's your job is to do that, develop something and then publish everything. Whatever you develop, whatever the innovative idea you came up with. That's a research wing. In the corporation, they have that one. So in a situation like that, if you want to come up with something, you can go with this one. And they try to come up with all of that, do the adjustment. You can think about how they can be adjusted without going the traditional path like this. See? You don't need that. See? That's the one that we're talking about here, that when it comes to the error term, we talk about this one in large scale yesterday, okay? And then we get the, not only that one, we talk about ANOVA table. ANOVA table not going to display that what we really looking into, especially the sum of square total. They not displayed over here, see, residual only, residual sum of squared. So you know the degrees of freedom, y is 394. N minus number of parameters. How many parameters in this one? B naught only. See, B naught is my parameter. Beta naught or B naught. So we have a 395 minus 1. See, this one 25,236. You're gonna divide this number by this number to get mean square. Every time you need the average. This is simply the average of the sum of squared for the. How do you get the average? You're gonna average. You're gonna divide by the number. How many times it has occurred? 394. That will give you this number. But we don't have a value of probability for certain reason. This reason, I'm going to install this now. Okay, let's go to supernova. Supernova, see, this will very nicely display everything. See? So we don't have a f. F is nothing but mean squared model. There's no such thing. Mean squared error. There's no such thing. Only thing mean squared error. Mean squared total is nothing but the mean squared error. Sorry, sum of squared error. This one, if you go to here, sum of squared error for the empty model, unexplained, leftover sum of the error, sum of squared error from the empty model. This one is same as the sum of squared total. If you go to another model, that's okay. When you go to next model with the absences being explained by what? The romantic relationship, still you have the same number here, same number. That's the total. Total not going to change. How the total going to change with the aid of that total not going to change, but you can split that one to decompose that into two parts. How much being explained by the suggested model? How much error being reduced by our suggested model? Or how much left over? Even after that you introduce that particular model, do we have a good fit for our data with the model? That good fit is completely decided by the pre-F, those two. These two. Not only that, there are so many other methods will be added later on. Okay. Goodness of fit is called, there are two areas called the goodness of fit and the lack of fit. Okay. Goodness of fit and lack of fit. Both we're going to talk about that one. So here that see. Now, if you want that one, you can bring it back that number and put it back into the formula. Absences equals mean value like that. See? Okay. The estimated parameter is the intercept, nothing but it represents the mean absences for the sample. Absences is the outcome for the individual, ith individual I, and EI is the residual for the individual I, means absences of the ith person. Ith one minus ith mean. Okay. Based on the model output and model statement, interpret the estimated parameter. See, parameters are the beta naught. And its estimated statistics is beta naught, which is how much? Which is 5.79, sorry, 7090. 7090. Parameter and statistics. Look at this. Parameters. Can parameters be calculated? This is estimated or calculated. You can say calculated. Parameters, but to be estimated. Those are estimated to be estimated. If you see parameter to be estimated, it's estimated. It has been now estimated. That's why I say statistics should be what? Calculated or computed. Know the difference between this, the difference between calculated and computed. Computed. Parameter is that something in that your population model, beta naught. beta naught, and its estimated statistics, sorry, to be calculated, which is already calculated or computed, or the computer has done that one for us. So that's 5.6. The estimated parameter is the intercept, and it represents the mean absences for the sample data. Therefore, the absences I is the outcome for individual I, and then you can explain another way. See? Explanatory model, two group model. Now add your explanatory variable to the model. See how is coded. Xi is coded as 0 for no, 1 for yes. It's been dichotomous. For the dichotomous, two options, no? See, binomial, see, or binomial, see, see, two terms, see, yes or no. So we can say what trial, it's a trial, two options. So you can write this way, see. Now you're gonna say mean absences for no group plus mean absences for yes group minus mean absence for no group times x plus error. X as we told over here, x would be either 0 or 1. So beta naught plus beta 1 plus x plus error. Absences y bar no plus y bar yes minus y bar no times x plus error. For absences, intercept plus slope. See, slope is nothing but this difference plus error. Absences b naught plus b1 x error. Or absences, you can say by x b1, I'm sorry, not bi, b1 times xi plus error I. For b naught b1 romantic, see, absences. Instead of that one absences, you can say y here. Y equals that one. When you use the formula, you can use the formula on both sides rather than writing that. Y. Y equals b naught this one. Same way y. Oh no, that one. We have that one. Then we can choose. Yeah, see, XOXI is coded as this one. Now we can run. See, now we're gonna run. And then we can get the romantic model. See, this is B naught, this B1. The difference between see, this is no 2 years. Okay, no, this no ones are coming first because we discussed that one the other time. And then see, now this time see, you have a 2 estimate, which ones are see over here again. See, look at there again, the error has the same issue, but it's almost like a right skewer. Okay, and then you have a 2 variable parameters. They have already estimated. It has been done many times, 1,000 times yesterday I showed. Then it will create some kind of a variation. That variation is given by this much. And in order to run a test, then you have to take the ratio between these two, which is that. Then you have to find the probability more than this one called p-value. See, that has been done for each and every one. They've been coded like this. 0, see, this one, this is 1, 2, 3. 1, 2, 3. If it is 1, 2, 3, see, you can simply say 0. Let's say here 1 and 2. You can easily, significance can be given by if it is 1 and 2. See, 0.001. If you see a 1 star here, if you see 1 star, it's a 0.01. Okay. Then if you see a dot, it's going to be 0.05. Okay. Or they simply put 0.1 and 1. That's what it says. This can be easily replaced by this one. That's what they say. You can simply say 0. This is 0, but if you don't have to think about deeply that when you're gonna move this decimal place to that 16 location to the left of this number, it definitely become 0.000000016 times 2. So that's almost 0. That's what they say. If you see 3 stars, you can call that one 0. If you see 2 stars, you can say it's almost like a 0.001. 001. Go with that one. 0.01. this one 0.05, then 0.1. Residual standard error. See, there are multiple R squared, adjusted R squared, F statistics. This one p-value, see, they were given up to a certain point here. See, F statistics 9.469, 1 and 390 degrees. You know what these are, okay? What these are, where are they? See, so did we run the ANOVA? No, let's run the ANOVA at the same time. Okay, look at here, ANOVA. Here, F value, it's already mentioned here too. If you run the summary, 9.469, 9.469. And the degrees of freedom, see 1 and 393, one for model, second one for error, 393. See, p-value, see, p-value, this one. You even displayed, if you run summary on that, you have the variable semantic model. See, then again, see, 2. If you have a 2, see, you can simply say 0.01. See, less than 0.01, less than, and you can simply convert at that 1.001. So then instead of that one, if you go to supernova, that will display everything. See, as I mentioned earlier, this is the same thing that you saw from the empty model. It's nothing but the sum of squared total is nothing but sum of squared error carried unexplained sum of the sum of squared error, unexplained sum of squared error, the leftover error that carried from the empty model. This is the sum of squared error explained by the model. This is the sum of squared error unexplained by the model. So that means a lot of that error, see, 20,000, 24,000, pretty much nothing has been explained by this one. Look at the pre, how much been explained? 593 divided by this one is almost 0.02. 0.02. And remember, we give the ranges for 0.02 for the pre. We give the beginning, we gave that one at a certain point for pre. That those ranges. I give those. We gave that one at a certain point. So pre is what? The pre. So you can remember that if you can go back a little bit, refresh your memory that so that your f, let's go to mean square, see, sum of squared error, sum of squared model. Oh, I like to call sum of squared regression. Sum of squared regression. Nothing but this one. See? This one is how we got that configuration. Can you remember? This one you can remember. Okay, I go to this one first. Sum of squared total. Sum of squared total. And I can go to sum of squared error. Sum of squared error. Or residual. Doesn't matter. How we got those. See, this one is pretty clear in writing, right? So this one, in this case, what is our relationship? Absences being given by semantic plus error. Or equal sign. If you put the equal sign, you put like this. If you put the absences tilde, you don't have to put that one. You don't have to put error. But if you don't put that one, absences equal. community. So this one you can remember that sum squared error means what? Summation of what and what? Summation of, you're gonna go ahead and then find the data point for what? Y means number of absences. No, this is Y, absences. This is X, this is Y, this is X. Then you can remember that people who say yes, number of absences minus what grand mean square plus summation of no people. Okay, I'm gonna put n, only n over here. N no 2y bar. That's one. You can remember that's how we got. This is for what? Yes. This is for no people. But this is a grand mean. It's a grand mean. This is the absences. Absences for years. Yes group. This is absences for no group. No group. See. Put over here. No. Okay. No group. That one. Then this one. How could you get this one? This one you get what? You go to Y. From this one, you're gonna subtract what? Y subtract. It's me. It's on me. Y bar of ES group. See, this is again ES group, but this time you go Y that ES group, but it's on me being subtracted and squared plus this one, but no group. You go to no group. From their reading, you're gonna subtract their mean. Y by square. That's that. This one, see, that reading minus grand mean. This one, that reading minus what? Reading minus see? This one. Yeah, me. This one is what? This interest. Again, ES group, you're gonna go to what? Y bar of ES group minus Y bar of that one. See, mean to me. That's for ES group. That's for no people. Y bar no to Y grand mean square. Like that. That's how you got this one. All these. That's how you're gonna display these numbers. They have done this calculation inside. That's how you got this one. This is SSR. This is SSC. This is SST. Okay. Then their degrees of freedom, can you remember? Degrees of freedom of total is nothing but n minus 1. So n is how much? 396 minus 1, 395. Do we see 395 here? 390. 390. How many people in this one? 395. Not 396, 395 in the data set, no? 395 in the data set. Sample size is 395. 95 minus 1. 395 minus 1, 394, no? 7, 394, see? So this one, see, SSR, SST is how much? Okay, I'm gonna get rid of this one and write it. 593. 593.11. It says error 24, 641.808. If you add those two, that will add to the total. Total is nothing but 25, 230, 235.519. This one and this one, if you add the SSE to the SSR, that will be SST. But on the other hand, degrees of freedom of error is nothing but n minus number of parameters. So you have n 395, number of parameters 2. Can you remember what are those? Beta naught and beta 1. Beta naught and beta 1. So this is going to be 593. I'm sorry, 3. I'm talking about what I'm writing. 395. Or something I was something in my head. 393. And the degrees of freedom of the regression is nothing but n minus number of x, in another way. How many? 395 minus, sorry, this one number of x. This is number of x. This is nothing but number of x, which is 1. 392. That's how you got this one. See, 1392. That's one. And later on, what they did was that they get the mean square. Look at the mean square. Mean squared regression. Mean squared regression. See, mean squared regression. No model. Same thing. Okay. Regression, no model. Same thing. Nothing but sum of square regression divided by degrees of freedom of this one. Then you get the mean squared error. Mean squared error. Sum of squared error divided by degrees of freedom of error. See? Degrees of freedom of error. Looking into this one, which is sum of squared regression is 593. See? 593 divided by 711 divided by 1, 593.711. Then the regression, if you go to 641.808 divided by 393, 393, you got 62.702. That's how you got those numbers. They divide this one. Then later on you get the F. How do you get the F? I'm going to call that an F naught, mean squared regression divided by mean squared error, which is 593.711. 711. I think that should be 711. 711. 711 divided by 62.702. That's the value we have over here. F for 9.469. 9.469. The other hand, that they were looking for the pre. Pre is nothing but r squared. R squared. R squared means what? Coefficient of correlation. Coefficient of correlation. Oh, I'm sorry. Correlation squared. Okay, coefficient of correlation squared. Or you're gonna say coefficient of determination. How do you determine whether this is going to be the best model or not? This one, proportional reduction in error. How much error being reduced by our model. So sum of squared regression divided by sum of squared total. So the sum of squared regression, you have how much? Sum of squared regression, you have 593 point and times 100%. If you want, you can go with 100%. Okay. You can go by 100%. See, you can get the percentage, which is 593.11 divided by your total is 590, 25, 23, 5.529, 519, no, 519, see, and times 100% is how much? See, that's the value, see, almost 2.35, 35%. Nothing has been explained. Nothing has been explained, see, 2.35. The other one, the last one, the F one is, you have F distribution. We're going to go to here, F naught. We know F naught is 9.469. See, this one, this area. See? As for the p-value, p-value is a probability. This is called the F distribution. See? F distribution with degrees of freedom regression, which is 1, and degrees of freedom error, which is 393. That distribution. So F greater than F naught, probability F greater than 9.469, which is almost 0. That's how you got the p-value from F distribution, which is right skew. So here that they say that when it goes to that tree, the ranges of the tree you can remember. Tree. What are the ranges? 0.01. The other one 0.09, 0.25. Okay. So this one 2%. I'm sorry. This, see, 2%, 2.35, 2.35. See, 2.35. It's a percentage. Okay, I'm talking about the percentage. 0.25, 0.02. I'm sorry, 0.02. Here we have 0.01. See, so it's here, this neighborhood. So my value 0.02 in this neighborhood. So this is another neighborhood. If it's like a 0.11, you can take like that. This one. So if this one, see, this one pretty large effect size. Say effect size. How effective this should be. See, this one medium effect size. This one very small effect size. There's no effect at all. That's the one that they've explaining over here. See, throughout this whole thing. Then here we can talk about this one down the road. Why it says the type 2 SS. There are 3 types of SS as well too. SS is not, that means here your SS, this SS to this SS, they get added to this one. But there are some other SS, sum of square, they do not add to this one. Okay, there's another one, type 1, type 2, type 3. See, sum of squared, you have 3 types. You're going to learn about that one in next class. Okay, sum of squared. See, sum of squared. See, type 1, type 1, 2, type 3 types. Like that. 3 types. We're going to learn about that one too. Later on that you will be that add more variables to that one. You cannot simply add. When you're going to add, you have to make sure that addition will be that explained by you systematically. First one you add and see how it works. And then if its effect is like not that much large, you can take it out. That's a stepwise from the process and all kind of stuff. But we will go to those things later on. See? So here we wrote that one, we brought that numbers back to that equation by running see 4.3. If you put this back, see, you have estimates, absences. See. When you write the estimates, actually that rather than writing absences, is the proper way of writing this one. See, estimated model. Look at that. I'm gonna write here. This is the model. This is the model you have. I'm gonna write with the y b0 plus b1x only. You don't have an error term in model. Okay, remember. Error term only in the equation. The without error term on the your right hand side, call the model. See this one. So this one you can write absences equals see, b0 plus b1x. See, x may be see 1 or 0, no romantic relationship. Yes, like that. Okay, now we have already see actually write like this, beta not beta 1. Now you're gonna write like this. See, if you want you can write like this. Look at look at what I'm gonna do. I'm gonna put a hat everywhere hat. Oh, this is y hat. This is called this is the model. This is the estimated model. This is the estimated model. See, that's the estimated model. You can put a y hat because the gap between y hat and y is the one that we will take into account at the end of the day. See, y hat. See, look at y hat. See, so you have see. I'm gonna write here like this. Complete. Okay, complete this one. Y like this. I'm gonna write one more time this one. This one. If I write like this, I have to write not y. That's the one that I want to emphasize. So expected value of y. Okay, I'm gonna write this one clearly one more time. Okay, I have to write very clearly. I'm gonna write this one in 2 ways. Okay. So what I'm gonna do, I'm gonna write the population version of the model. Okay, if I write the population version of the model, I'm gonna write the model only, model part. Okay, I'm gonna say expected value of y, beta naught plus beta 1x. This is how you have to write. Plus, okay. This side, population version of the model. I'm gonna write expected value of y is beta naught plus beta 1x. Expected value. This is nothing but expected value. Value of y. They say expected value means if you're gonna do something in a long run, what you're gonna get on average. Okay, that's the expected value or expectation. Expectation of y. That's expectation of y. This one has a this one has a 1. Yes, romantic relation. This one 0, no. Okay. Okay. Counterpart, if you write that sample version, see, sample version of the model. Okay. You have to write this way. Correct. Y hat equals B naught plus B1. That's what I want to tell you. This one, yes, this one, 0, no. So that means absences estimate. Y hat. If you write like that. So that means that if you write this way y hat, you're gonna write that B naught. You already have B naught value. B naught value is how much? B naught value is, we got that one already. B naught value is 4.840, 4.840 plus B1 2.599 times 6. See, that's how you have to write. Okay. Now, how do you find the error? Now you're going to write that equation of the model. See, I'm going to write here something. Equation of the sample version of the model. Sample version of the model. All right, the equation. It say y equals y hat plus b. That's the idea. That's how you're gonna write. That means in another way, y equals 4.840 plus 2.599 x plus error. Error term has been explained. Okay. Therefore, if you need the error, error is nothing but e is nothing but y minus y hat. That's what I'm trying to say. Okay. Y minus y hat. That difference is called error. Okay. It's the model. It's the equation of the model with the error. If you put to here like that, that's okay. But if you need the error, you subtract from here simply y minus y hat. Okay. If you write like this way, make sure to write absences hat. Absences hat equals 4.840 plus 2.599 romantic. See? So like this way. So like this way. See? This one you can write like this. See? This is data. This data. This is the estimated model. Sample version. So here, if you write with that equation of the population model, see, equation of the population, see, population version of the model. What do you get? See, you get y equals ey plus epsilon. That means y equals beta naught plus beta 1 x plus epsilon. See, okay. See the difference. Here you're gonna say y equals ey plus epsilon. That's why you cannot do nothing here. Everything you do in the sample version. Remember, this is the key part. This is based on data. See, data. It's everything based on data. Data you're gonna utilize in order to do all these. This part, see, you cannot do nothing. See? Abstract, very abstract. Abstract, theoretical. This is empirical. See? This part empirical, data part. So that's how you're gonna write. The error means the error. Error means epsilon. See? This is unknown. It's become how much? Estimate B naught. This is unknown. You estimate. You call B1. Those values do you know? These are to these are called parameters. Beta naught and beta 1 called parameters. B1, B naught, B1 called statistics. Beta naught and beta 1 are parameters. Parameters. If they're parameters, what are you going to do? To be estimated. To be estimated. And their counterpart, B naught and B1 called statistics. What are you going to do? To be computed, calculated. or computed. So simply B naught hat is B naught, B1 hat is B1. Right, the data one naught is B naught, data one is like that. That's the idea, estimates. Okay. So that's what we were talking about here. Okay, that's okay. So then see, no, nothing, the model part is an empty model. Okay, then we did this one. Then we looking into that supernova. You saw even a supernova model. Now that you have estimate of your parameter, put them back into here. That I wanna say that this one absences. I'm gonna add something to. I'm gonna say this gonna be on top. That's why I'm gonna say hat. Okay, hat then underscore I equals romantic plus model statement. I don't need the EI. Okay, I'm gonna get rid of this one. That's the model statement. Model. Okay. I'm gonna call that one model. Okay. Then I can make it clear this one. That's the model. Okay. Okay. We'll go over there. I'm gonna say the model equation. I can say like that. Model equation in the sample version, I can say absences. Okay, now you can say absences equal this one plus error. E underscore I. That's the idea. See, this is y. This is y hat. Okay. You can say y. Sorry, y. This one hat underscore I equals this one. This one is not y hat. This is y. Y of I equals that one. Okay. Therefore, you can say error. Error is nothing but y I minus y hat I of the I person. That's the idea, which is EI. Error equals EI. EI equals this one. To make it clear. Based on the model output and model state, interpret the estimated prime. What the numbers mean. See, you know what these numbers mean. Okay, you can see estimated prime is line, intercept, and slope. Blah, blah, blah. Then what? Comparing the two models. How do you compare two models? See, create an APS supernova for your document. Discuss your. Okay, you have a supernova already. You run this supernova. We have that one. We're gonna utilize what? Pre. See, pre. So I'm gonna go ahead and look into this one very clearly. Workflow. See. Okay, if you go to the introduction and research, we done. Data, we done. Provide a visualization, we done. Empty model, we done. And here, now that you have estimated based on the model of statement, interpret the estimators comparing this one. I'm here. Okay. What is the proportion reduction and what does it mean? What can you say about the strength of the model from prior? What is coherence D? Okay, those are the ones we're looking into. So you can explain the same. The sum of squares is 25, this one, degrees of freedom, this one, and mean square, this one. There's nothing in the model and error proportion because in an empty model, whereas in the romantic model, the data is there for the model error reduced by, see, total, see, empty model. First one, creator. I'm going to have a look at this question one more time. Okay, comparing part C, comparing the two models. In number 3, part C, create an supernova in your document. Okay, that's okay. Create an AP. of the supernova table in your document, discuss your findings. Okay, supernova, we run this one, we have. Then you can discuss that one, what you see from that one. Okay. Oh, which model? Empty model. Sorry, empty model. Okay. And then the other one for the romantic model. Okay. So you can discuss about that one. And then same way that there's nothing in the model and there are portion because it's an empty model, whereas in the romantic model, the data is there for the model error reduced, error from the model and total empty, total from the empty model. So I'm going to add something to here very clearly. So whereas in the romantic model data, the data, sorry, whereas in the romantic model, the data is there for the model. Okay. Error reduced. It's not right. Okay. Error is this one and total is 0. Okay. The whereas the data is nothing in the model and there is an empty model. Empty model. Whereas in the romantic model, the romantic model can talk about this one actually sum of squared, total sum of squared. I'm going to add something. Total sum of squared, total sum of squared, oh sum of squared total, oh sum of squared total, oh sum of total, which is given by SST, is that much with degrees of freedom, with degrees of freedom 394, and mean squared is mean is and mean square is 6450. No, mean square is not 64, no, in the empty model. Empty model. In the empty model, the total sum of square, the sum of square total, which is SST, is this much with degrees of freedom 394 and 64. What is 64? 64 in model. So I'm gonna run this one more time. I'm gonna run. I'm gonna run this empty model. Empty. And I'm gonna run romantic model as well. Empty. Model. Okay. 5.79 to this one. It's 64. The mean squared error, okay, mean squared total, okay, mean squared MST, mean squared total, total, which is mean squared total MST is 64. Good, okay, 64. you know how to get the mean square, sum of square divided by the degrees of freedom. Okay, that means this number has been divided by this number. See, 25, see, 235, 519 been divided by 394, 394. Give the mean square total. Okay, on the other hand, there's nothing in the model, an error portion, because it is an empty model. Okay, good. Okay, whereas that in the romantic model, the regression sum of square, regression sum of square, which is SSR, SR regression sum of square, from model sum of square. Okay, model regression sum of square. Yeah, model sum of squares. The other one, error sum of squares. SSC and SST. And total sum of squares. ST. Numbers. Okay, if you want, you can put the number. Here, model or equation, sum of squares, SSR, error, sum of squares. So I'm going to add to here something. That's the key part. SSE. I'm going to go to SST. SST. SST is nothing but unexplained. Unexplained. See? Unexplained. Leftover error. Error from the empty model. Empty model. See? Unexplained. Unexplained. Leftover error from the empty model. Okay, another way to look at it. And then SSR, explain error, explain. Okay. Explain error by the model. Okay, by the model. Explain error by the romantic model. And SSE, I'm sorry, SSE, nothing but the unexplained error left over. See? Left over from the romantic model. From the romantic model. See? Oh, sorry. Romantic model. See, that's the idea. See? So if you want to see that so if you want to look into the tree is nothing but tree is nothing but sum of squared error divided by sum of square regression divided by sum of square total. That means what? Explain this one, see? This one, explain this one, see? Explain error. We see that one divided by see unexplained error left over from the empty model. See, another way to look at it. And on the other hand, F, what is F? F means nothing but, F is nothing but mean squared regression divided by mean squared error. That's nothing but sum of squared error divided by degrees of freedom of sum of squared regression divided by degrees of freedom of regression. Okay, regression divided by sum of squared error divided by degrees of freedom of error. Okay, which means, see, so SSR means this one, see, explain error. See, explain error per degrees of freedom, see, per DF, per degrees of freedom divided by, see? And the other one, and this one, so unexplained error. Sorry, this one unexplained leftover error. Leftover error. Error. Per degrees of freedom. Okay, that's the idea. So you can explain like that. So that's a division between those two, unexplained error. See? Leftover error. Sorry, leftover error or leftover from that on this. Per degrees of freedom. So how could they gonna change from each other? They look like there's a ratio between the sum of squares, but here only difference that in F you have a per degrees of freedom. It has been expressed in per degrees of freedom. Okay, per degrees of freedom. Okay, that's the idea. So what is the proportion reduction? So then they're gonna ask that what's the proportion reduction? That means TRE value. We saw that on 0.023. See, see what is the Cohen's D? Cohen's D, you can get that by installing this one, LSR, learning statistics with R. Okay, library. And if you go to this one, you run this one, and then pretty much everything here. Okay. That's okay. Yeah, I'm gonna run this one, semantic model, this one, and B naught. If you want B naught, I'm gonna run back again. B naught. If you get that message, they say that it's not automatic. They say it's gonna be that. See, another version. See, this one. This the function is moving to the Coscata package soon and will no longer be available in the Supernova package. It's under the Supernova 2 that I have this one to show you something. Oh, I don't need to do this one twice again. I did that one already. Equal to do this one, okay? And then we can get the B1, B naught. See, we got the B naught. We can call the B naught. We can go here and then see. like that way, or you can run like this way, see, or B naught of that one. B naught is keeping as a like a function, so that by running that the model inside that one pre, like this. See, one more time. See, this one. That's one. See, and cohens D. See. That's why was the coherence D, and what this mean? What can you say about the strength of the model from the coherence D? See, this is the mean difference between. See, you can get the coherence D. So you can see this one. It's mean difference between those in a romantic relation versus the not in. It's very small. The mean number of absences for their romantic relation is only about 0.328. Standard deviation unit larger than those who aren't in a romantic relationship. Okay, then you can explain this one, conclusions and everything. This one, let's see, where is this one? Coherence D. We have a coherence D, coherence D, coherence D, coherence D. Okay. This one. Favorite statistics, romantic statistics, this one, then ANOVA table, coherence D. We got that one from here. Coherence D, we're gonna try to get this one by hand. No, okay, that's what we're trying to do. Okay, this one, the F function, see, R and Q, see, we know probability of that one. So this is the way that the probability of getting 9.469. This is what I was showing over here. This is exactly. Okay, see, if you want, you don't have to, but see, this is the way how I'm gonna. So this one you can evaluate. It will be displayed along with your. It is definitely in your supernova table. Okay, it's already in supernova table. You don't have to worry about that one. It's already. But what I'm trying to say that by any chance that if you really want to find something that some kind of probability more than a certain number, this 9.469, we're going to do that by separately here. How? That's what I'm discussing here. See, I'm getting that probability of that particular distribution. T means the probability of F distribution. If you have a normal distribution, can you remember we put the T norm instead of T norm? That's for the normal distribution. For this distribution, you can put this one. You put first the cutoff value. This is the cut value. See, for 9.469. The degrees of freedom. This one for numerator. Degrees of freedom of numerator is nothing but the degrees of freedom of the model. It's the degrees of freedom of error. And lower tail, I'm going to say, don't give me the lower tail. I need the lower tail. No, I don't need the lower tail. I need the upper tail. That's what I'm trying to say. I need this side. Otherwise, by default, they're going to calculate this side. Then you have to subtract from 1. Okay. By default, they're going to try to calculate this side. That one I'm going to prevent by giving this command and say, hey, I don't need this one to that side. See, 0.0022. That's the same thing that you saw with that. If you're going to run that one supernova, I'm going to run supernova here. 0.0022. 0.0022. There's actually 0.00223610. It has been expressed into 4 decimal places over here. And if you need some kind of a random numbers, you can do that one. So what I'm gonna do, if you want to generate numbers from that 100 numbers. If you want to generate, if you want to extract, like I'm talking about simulation, if you want to extract 100 numbers from this guy, you can use this one. That's the discussion. See, it's called the random form F100 numbers, degrees of freedom. I'm using a different kind of degrees of freedom. This non-central, the non-centrality parameter should be 0. That's why it says. See, these numbers extracted from that one. Okay. On the other hand, if I put that 0.002 back to this one and find that cutoff value, I can get the cutoff value back again by using QF quantile. See, 9.469. 9.469. That's for the probability. See, these are for the normal distribution. These are for the T distribution, like that. Okay. Anyhow, that's what I was trying to do. Here, that what we're gonna do, we're trying to calculate that Cohen's T with the by hand. Okay. So you don't have to, but I'm showing you that. So those are the things. This is gonna come in like a matrix because the favorite set absences was romantic, and then you're gonna run this one. You saw that mean and the B0 and B1, and then you go to the ANOVA. ANOVA I'm going to assign to this one. See? If you go to the ANOVA, that residual and mean. Okay. I run ANOVA. That one I'm going to residual. See? If I read for that one, say please go to the ANOVA and residual and mean square. Give me that value. That's nothing but 62. See? This one. This value. Okay. And Cohen's D, see, if you run Cohen's D, okay. So I'm going to call that one D node, 0.328. It's nothing but you go to the romantic state, go to the 27, which is the mean, see, second one. So I'm here. I'm here. Yes, the mean. See, you go to the which column? 1, 2, 3, 4, 5, 6, 7th column, and then you are reading. It's mean minus romantic stat plot 17. 17 means no. 4.84 divided by what? Divided by S. You can remember that formula. You can remember that formula. We had that broader discussion on that one. You can remember that Cohen's D. Cohen's D is nothing but, see, Y bar, yes people minus Y bar no, divided by this one. You decided to pick different S for that one based on the situation. I told you root, mean, squared, error would be the best one, which is mean squared error square root. See, that's the one. In addition to that one, there are some other methods too. We have already elaborated those ones. Okay. So I'm trying to use the mean squared error. Same as what if you use the pool one. You can remember you can use the pool one here. Or you can use that if the sample sizes are the same, you can use this one here. The mean of those two divided by the standard deviation, the variances, and let's take the square root of that one. Or you can use the pool one. So if I'm going to use the root mean squared error, so that's why I was trying to get the mean squared error here. See, I got the mean squared error. I'm going to go ahead and say, hey, whatever I call this one, see, this is the mean square. Take the square root of that guy. Okay. Like that way. Oh, what is the other one? Other one is what using the other formula. Other formula is what's the other formula? What's the other formula? Other formula say you go to the square root of, see, I'm trying to get the spool first. What is the spool? See, you can remember spool. Instead of S, you can use what? A spool. Spool is nothing but, see, nothing but degrees of freedom of ES group. The ES group's standard square, the variance, no group degrees of freedom, no group square that variance divided by the degrees of freedom of ES plus degrees of freedom of no group. So that's the same thing. See, a spool is nothing but, so the degrees of freedom of ES group is nothing but number of in the ES group minus 1, that is variance, plus number of in the no group minus 1, No groups variance divided by ny minus 1. That one means n no minus 2. That's the one that I'm utilizing. I'm gonna recall that one. See, I go to this one and recall it. See, I'm gonna go to square root. I'm gonna say go to the romantic stats and go to the 2 and 9. 2 and 9. What that means? 2 and 9. Ninth one. See, 1, 2, 3, 4, 5, 6, 7, 8. 9 means degrees of the size. 263. I'm gonna recall that one. See, 9 minus 1 n minus 1 times. It's what? It's a standard deviation. I have squared that one. Plus, go to the romantic stat and go to the people who say no. Number 1, 9. 1, 9. See, 1, 9 minus 1 times romantic stat standard deviation square divided by romantic stat n. People that who say yes, n, how much? 260, 132 plus 263 minus 2. Another way to calculate that. That's what I did. If anybody wants to that, then you get the spool. That's a spool. Then you go to the Cohen's t is nothing but romantic stat 27. That means the mean. Yes people mean minus no people mean divided by a spool. 0.328, same number. Same number. The standard deviation of this my data go to absences. See, another way to look at it. See. Look at this one. It's absences. See. Standard deviation. What is that one? This is the standard deviation of the data regardless of your that what? Regardless of your what? The gender. Sorry, yes or no. See, I simply go to the absences standard deviation. Then I go to the ANOVA table and I'm gonna see, I'm gonna run that one. Then I'm gonna say from the ANOVA romantic sum of the, I'm gonna run this one for you. ANOVA. See, it's like this. I'm gonna go to the romantic and then I'm gonna go to his part, sum of square. See, 593, and this one is 593 should be. I'm recalling that one. Okay, that one. Then I'm gonna go to the residual one. Is P. See, which is P. See. So that B. Then I'm gonna get the total of that one, which is that one. See. See. Total. See, that's the total. See. Then I'm gonna go ahead and get the mean squared. See, T. T means what? See? T. I need the mean square. This is the sum of square total. Sum of square total. I'm gonna divide by what? Divide by degrees of freedom. See, degrees of freedom. Its own degrees of freedom is n minus 1. Capital N means like a capital N means like the sum of both kind. Okay, which is mean square total. I take the square root of that one. Root mean square error and the number of absences. See, root mean square error. You can get another way. See, that's a S absences. I think we already did that one. See, root mean square error. You can take like that. See, that's the root mean squared. You can utilize here. See? Utilize here and then do that one again. Another way to get the root mean square, but mainly that if you are that interested in this thing, Cohen's d, that one or one shot you can get with the Cohen's d. So conclusion, see that the other rest of you can write. Okay, you can write the rest of the to complete this one. Okay, let's go ahead and look at that our this one, the final exam. Okay. The homework come along with this one. Okay. Look for no. Where is the final exam? I got that one. Okay, that's okay. I can show this out again. Someone final. Exam only chapter 7 review questions. Okay, say student survey is a data from the 362 observation on the following 17 variables. Okay. 17 variables. They were using 17 variables. Year, gender, smoke or not, award, higher status, exercise, TV, height, weight, sibling, birth order, verbal, etc., GP, false and piercing. I think we have seen this data set earlier. Okay, we have seen very clearly this data set long time ago. Okay. So let's look at the number of hours spent exercising per week by the sample student. Okay. See. Yeah. Yeah. Histogram. See this one. They ask what we might see. Why might the mean be a good sample model of this distribution? You know the reason. Because the mean is the only statistical? No. Mean is the most frequent? No. Mean because the mean because all skewed distribution, the mean, no. Is that the reason? See, this model because it's different from the median. See, because the mean is a model that balances the deviation from the model and minimize the sum of squared residual. Okay, this is the reason. Okay, this is the reason. Okay, that's the reason. Then what? If you use this code to fit the empty model, see, and then use the predict. If you use this one and if you predict that one, what do you get? It would depend on how much they actually exercise. The value would be the mean. The value would be the mean number of hours exercised by the sample and would be the same for each student. You would not be able to determine this one. No, you would. That would be the what? C. No, that would be C. No, thank you. Yeah, 2C. Yeah, thank you. Yeah, 2C. The value would be the number of number of hours exercised by this sample and would be the same for all the students. So if you go to number 3, having a low resting heart rate recorded in the variable pulse is supposed to be an indicator of good cardiovascular health. Let's say we wanted to create 3 groups based on pulse, low, medium, and high. Which of the following code would do that and save the values in a new variable called pulse 3? Pulse 3. 3. Yeah, 3B, 3B. Yes, student survey, pulse 3 group, entire. See, divided by entire, that's B. Okay. 4. Which of the, sorry, see, which of these options could be used to depict the relationship between exercise and pulse? Pulse, no. 4. Which of the option could be depict the relationship between the exercise to pulse, exercise, and then student survey? No. See, and the facet grid by the pulse 3 group, student survey, exercise from the GP points, that means all. Yeah, thank you. Yeah, that's all. We are going to try to this one D. Okay, we are trying to go to explain a variation in exercise hours with the cardiovascular health pulse 3 group. Assume our model is like this. If we write the model in GLM notation, which of the equation represent the pulse 3 group? Which one? Number 5. How many variables do you really need if you have a 3 option? 2 option, you need 1 variable. 3 option, you need 1 less than that one. You need actually 2 variables. I showed you all the time. So what do you think? It should be this one, okay? Should be this one. See, can you remember that powers? They say they have a three. They're gonna say medium. I'm sorry, I'm gonna go back to this one. Low, medium, and high. See, low, medium, and high. Can you represent that one? Exercise by pulse 3 group. Pulse 3 group. Okay. See? So see, they're gonna do the exercise. See? By pulse 3 group. So in order to write this one, you need a y equals, this one has how many options? Low, medium, and high. This is categorical, okay? This is a categorical one. Cat is quantitative, no? Quantitative. Now what? Now you're gonna write this equation y equals, see, if you write the sample version, estimated one actually b naught plus should be, as I mentioned, if you write with the b naught, the proper way of writing this one with the hat. If you don't put the error, if you put the model, I'm gonna write the model only. See, model only. B naught b1 x1 plus b2 x2. That means x1 can be what? I'm gonna bring this one down to what? Actually, I'm gonna write this way, okay? I'm gonna write this one clearly for you to see. I'm gonna write one more time. I'm gonna write like this way. First, y hat equals b naught plus b1 x. That's the way how I write. But we have an issue. The issue means this one has a 3. Sorry, you cannot do that one. So this one has a low, this one has a medium, and a high. See? And this one is a categorical variable. See? So since it has like a 3 options, we cannot simply use x. I'm gonna replace x with a what? Indicator, 2 indicator variables. X1 I'm gonna split into 2. See? X1 and X2. Is both are what? Indicator or dummy variables. See, so then because the x1 can take what? I'm gonna denote this one 0, 1, 2 like that. Right? For my convenience, 0, 1, 2. See, now come to this one. You're gonna say if x can take either 1 or 0, x2 also take 1 or 0, but if you put these together and looking into this one, you're gonna say x1 means what? 1, 0. X2 means what? 0, 1. That's the idea. If you need x2, you have to put 0 and 1. Okay. If you need the x1, if it is medium, see, no? If it is a medium, you can say what? The where is now 0, 0. Now you might be thinking this is for what? Medium level. This is for medium. This is for what? High. Where is the low one? Low one is where? Low one is nothing but what? 0, 0. I'm talking about x1 and x2, okay? Just as a, see, this one, x1, comma, x2 together. X1 and x2, you're gonna look at the together low, together 1, 0, together 0, 1. Separately, they can take values 1 and 0. That's true. Now you are missing one option, 1, 1. There's no way you can put 1, 1. There's no such thing. Be careful, okay? There's no 1, 1. You might be thinking why you say that 1, 1. Yeah, but this option, there's no this option. There's nothing can be described by that 1, 1 in this stage because these are dummy variables. 1, 0 will say together x and 1, x2, together 1, 0 says that you are talking about medium level. Together 0 and 1 for x and 1, x2, it's talking about high. Together 0 and 0 talking about low. Together x1 and 1, there's no such discussion. Okay, that means like let's say that you need the low level, you're gonna put what? 0 here, 0 here. See? 0 here, 0 here together. See? 0, 0. Then if you need the medium, you're gonna put what? 1 here, 0 here. If you need the low, you put what? So I'm sorry, high, you put 0 here, 1 here. That's the idea. That's the idea. Okay. So simply see, for low, you're gonna put what? X1 and X2 together, 0, 0. Then you get what? Y hat equals B naught. only. Then for medium, for low, for medium, x1 and x2 together you put 1 comma 0. Then you get y hat equals b naught plus b1 x2. Sorry, b1, b naught, sorry, this one, b naught, that one. For high, 1 comma x2, 0 and 1, y hat is nothing but b naught plus b2. If you draw this one, you can see clearly this one. See, y is exercise. See? This one low, medium. See, this one high. High. See. So what? See? So we have a something here. We have a something here. We have a something. See? So this gap is b1. This gap is b2. This is nothing but b naught. B naught. So B naught is nothing but y bar of low group. This is the y bar of medium group. This is the y bar of high group. Okay, like that. For unit 3. Okay, this is C. Okay. And then this is C. This is, let's go to 6. Okay, we are going to try to explain the variation exercise hours with the cardiovascular health pathway. Assume the model is like this. Exercise equal positive plus other stuff. If we write the model in GLM notation, what does Y represent? Each person's value for exercise. No, each value for exercise. Hey, thank you. Yeah, thank you. So part, see, here is a depiction of the relationship between exercise pulse 3 groups. See, they are graphical representation. So when pulse 3 is included an explanatory variable in our model in exercise, we get this as our output LM. Exercise, this one, student survey. Is the output. See? Is the output. Interpret the minus 3.14. Minus 3.14. This one. Interpret this one. 771 is B. Thank you. Yeah, this represents the difference in average hours of exercise for people in the high pulse relative to the low pulse. I just mentioned that one. See, just mentioned. See? Low to high, not to the medium to high. Okay, low. Everything has been with respect to that one. See, in YI X1I blah blah. What does X1I stand for? I mentioned that one a few minutes ago. X1. Forget about I. X1 means what? In which group? What does X1 stand for? What is X2 stand for? X1 for what? People who are in medium group. That's why we put the 1 for this one. People who are in high group. So what? X1 means whether someone is in the medium pulse group or not. Okay, because this one can take how many values? 1 or 0, as I mentioned here. See, it can take 1 or 0, whether he's in this says whether any person be in, whether the selected person be in this group or not. If they in group 1, if not 0, that's the idea. Here, whether these people, anybody that selected person in what? A high group or not. If yes, 1, if no, 0. Okay. The answer should be that whether someone is in the medium pulse group or not. Yes, 1, not 0. That's the idea. So 8A, 9. See, 9. What do you think 9? When pulse 3 is included in our model to explain variation exercise, how is the error from this more complex model calculated? Yeah, 9B. 9B, the deviation of each person exercise from the mean exercise of their pulse 3 group. See, when is included in our model to explain the variation exercise, how is error from this more complex model? Error is nothing but the deviation of each person exercise from the mean exercise of their pulse group, each group. Okay, each group. So the deviation is nothing but what? You go to this one, your data, see, whatever the data you have, see, 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 see. Let's say these are, I'm going to call the Y of low group. These are Y of medium group. These are, I'm going to call Y of high group. Look at that difference. That's the error. Error for high group. This is the error for what? E for, I'm going to denote by that one, E for high group. This is the E for what? Medium group. This is the error for low group. Okay, like that, the error. One of the errors. Okay, there are 3 types of errors involved with that one. But if they when the Parseval's model explain variation in excess, how the error is from complex model is calculated. That means they are referring to error here means like what? The sum of squared error calculated with respect to each one's the means. Okay, so that should be definitely be. Thank you. Yeah. See the number 10. Number 10, when you add an explanatory variable to a model, what should be the effect on the sum of squares from the empty model? It should remain unchanged. What? Sum of squares, they refer to as sum of squares what? This is the issue. When you add an explanatory variable to model, what should be the effect on the sum of squares? Sum of squares, there are 3 types of sum of squares. Sum of squared errors, sum of squared regression, sum of squared total. They call the sum of squares mean for what? Sum of squared total. Okay, that's why they don't very very clearly talking about that one. I'm talking about here. See, they have to mention that one very clearly. See, sum of squares, sum of squares. See. There are 3 types: sum of squared total, sum of squared regression, sum of squares error. 3 types. But they simply call the sum of squares for this guy. This guy in the book here, 10. That's why it's 10A. Because it should remain unchanged. Sum of squared total not gonna change. You saw that one very clearly earlier. Whether you add anything, the sum of squared total is nothing but the unexplained leftover error from the empty model. Okay, so it's unchanged. So number 11, see, again, now you know, see, if we express our model, then which part represent the model prediction? Now you know, see, this is called the prediction part, this is called the model. Model is the prediction. Thank you, yeah, B. C, I'm sorry, C, 11C, yeah. The number 12, if we can calculate residual from the both empty model and the complex model, what is similar about these 2 sets of residual? Both are, see, the residual represent the difference between the data and the model's prediction. That's right. Model prediction is nothing but the mean. Okay, again, model prediction is nothing but the mean. See, if you go to the model, see, if you go to the y hat, see, y hat of that, let's say that low is nothing but y hat of y bar, sorry, y bar of low. Y hat of medium is nothing but y. This one is their mean. See, mean of the medium group. Y hat of high group is the y bar of high group. That's the same thing. That is the mean. The residual represent the difference between the data and the model's prediction. So the model has predicted what? So when they put together, and then I'm going to put everything together, you know that at the end of the day, this is the model. See, you can remember the model. Model is y hat. Y hat means b0 plus b1x, b2x2. See that one. Then error is nothing but, then you can write the equation. Equation is y plus y hat plus c. Then the error is nothing but e is y minus y hat. Okay, y minus y hat equation. that's right. See, this is called the predicted value. This is called the data. Okay? That's right. 12B, the residual difference between the data and the model's prediction. Number 13. Number 13. Imagine that you have calculated SS for both the empty model and the complex model for exercise. What will be the true about SS? 13. SS leftover from the empty model will be greater than SS leftover from the complex model. SS leftover from the empty model will be smaller than SS leftover from the complex. SS leftover from the empty model will be equal to the SS leftover from the complex model. In both cases, SS will be 0. Okay. I'm talking about leftover, okay, not the same thing. SS leftover, sum of squared leftover, sum of squared error. Okay, sum of squared leftover from the empty model. Empty model will be greater than the sum of squared leftover from the complex model. Complex model. Who sent who? Yeah, that's right. Yeah, that's part A, because that SS leftover from the empty model. The empty model is larger than the SS leftover from the complex model. Okay, so this is SS leftover. Simply, what is SS leftover from the empty model? This is what they say. Okay, here then you have a model. Okay, you have a model, you have an error, you have a total. Okay, I'm going to focus only on the sum of squares. See, let's say this one A, this one B, this one C, like that. See this guy is this guy nothing from the empty model. This is from the empty model. From the empty model. Empty model. This error from where? From the suggested model. From the suggested model. See? So this number and this number, if you compare, who is bigger? C is bigger than B, that's what to say. Okay, 13, that's why 13, yeah, thank you. 13A, because of that reason. Sum of leftover from the empty model is greater than the sum of squared error. See, sum of squared, see, error, leftover error from the empty model will be greater than the sum of squared error leftover from the complex model A. Okay, so number 13, number 14, we can calculate residual from the complex model and the mean residual from the 3 groups in this code. Okay, residual receipt from this one. If you get the go to the receipt residuals, you get the mean. That will give the mean squared, the mean of those. So the residuals, okay, these are the residuals. This low group, medium group, high group. I'm talking about residuals, okay, and their averages. Okay, have you done something wrong in R? Have you done something in R? No, mean always balances the residual. Thank you. Yeah, because that this is 0. It's 0. See, mean of each group would be 0. See? So that's the interesting part. This is what they are trying to say. They're trying to say you're going to see this kind of stuff, this phenomena later on down the road in other classes. Let's say that you have a low group, medium group, high group. See, they say if you go ahead and look at the residuals, I'm talking about the residual E of L group. I'm talking about the E of medium group. I'm talking about the errors of high group. If you go ahead and look at their error, if you draw like a histogram for that one, says they're going to be balanced on 0. See, 0. I'm just just thinking that this is my 0 line. Okay, doesn't matter. See, 0. So does with this one. Now you might be thinking, see, this one, see, all 3 errors. Error of M bar is 0. Error of high group bar is 0. Error of low group bar is 0. This is 0 line. 0. Now on the other hand, this spread, that's the mean. This spread, are they the same? That's the question we have. That's a very serious question. See? It's called the Beheron-Fisher problem. Beheron-Fisher problem means that's the when they have an error, are these three groups will have the same distribution, has the same variations. See, that means I'm gonna this is the mean, okay? Mean of each group, mean. Let's say this one, see, standard deviation of low group is a standard deviation of the medium group. It's a standard deviation of the high group. Are they the same? Standard deviation of low group equals to standard deviation of mean group. Standard deviation of high group. We're gonna say that what it is homoscedastic. Homoscedastic model. Homoscedastic. If they differ from each other, SDH, heteroscedastic. 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 It's a very big thing. It's a very heavy that problem that the people trying to resolve for long period of time. When they have they came up with a different. That's why Fisher involved. Fisher is considered to be the father of modern statistics. He involved. Fisher, that Beheron and Fisher, they combined together that try to resolve that one for a long period of time. See, this one heteroscedastic. We're gonna do this one. We're gonna consider this one for mathematical tractability and easiness. But in real practical application, you have like this heteroscedastic. If you're heteroscedastic, this formula, whatever that we use so far, not gonna work. It's getting a very serious issue. People did that one assuming that they have the same variances. They built up all the formulas. That doesn't work. But for mathematical tractability, we're gonna assume like that at the primary stage. So here means like this. If you get something like this, as she said, that the residual, see, always balances the residual. See, mean always balances the residual. Okay, number 15. See, imagine that you have both the empty model exercise and the complex model for exercise, the model that includes this class. What would you do if you wanted to compare how well they predict exercise? See, compare the SS from each model. Look at the reduction in error in the pulse model. Examine the pre. You can remember, you can compare the SS, yes, from both models and see which model gonna reduce the sum of squared error. See, any of the above. Thank you. Yeah, any of the above. Any of the above. See, examine PRE or look at the reduction in error. Reduction in error is nothing but the PRE in other way. See, compare what? Sum of squared error or sum of squared. Any sum of squared. You can compare the sum of squared errors or sum of squared model, or not the total sum of squared. Total sum of squared not going to change. SST not going to change. You can compare SSR from both models. SSR and see which model is going to explain more. The better model would have that more explanations. That means like more variable, more higher number. If SSR is greater than, it has a higher value in a one certain model, that would be the best model compared to the other model. If SS error is less in one model compared to the other model, that would be the best model. Okay. If you go with the SSR, pre the same thing, F, same thing. So see, SSR1, see, you're gonna say SSR1 from first model and SSR from the second model. If this model has this one, see, this model what? Beta model, this one. See, OSSC less than SSC of the second model. The beta model is what? 1. Pre greater than PRE2. See? What? The beta model. See? Whichever the model has the higher PRE and the SSR will be the best model, and then its counterpart, that SSC, if you're going to compare the model with the less error, would be considered to be the best model. Okay. That's how you're going to, at the primary stage, you're going to check that one, which model would the best model by comparing these. So the 15 should be any of these can be compared and contrasted. So look at here's the supernova table. See, for that our pulse 3 group. Interpret the pre. Interpret D. I'm sorry, I'm on 16. I'm on 16. Yeah, 16. 16B. Yeah, thank you. Yeah, 0.05 of the total variation in exercise hours is explained by the pulse group. See? See? Total variation. That means total one. From this one, how much being explained by this model? Pulse group. Pulse model. See? 636 divided by this one. So B, 16B and 17. Does this show that cardiovascular health, that is being a lower pulse group, causes student to also exercise more? No. That's D. No, because the design of the study was correlational, so we cannot determine the causation. That's true. We can come for like some kind of a correlation between what and what. What and what? The exercise and the pulse. Okay, that's it. We are not the expert to that explain the rest. Rest is up to the people in the medical field. Okay, they will decide the rest here because we are just study only the correlation. We are having a correlational study, not the causation. The cause for that kind of a thing will be decided by the rest. So part D. Okay, that's the answer is D. Sorry, D 18. So then we stand here's the supernova table again, that formula Pearson versus pulse 3 group. Why does this table have a smaller sum of square total 1699 than the supernova table for exercise explained by the pulse 3 group? Exercise explained by this one. Now here we have a completely different one. No, we have what? Pearson was explained by the pulse 3 group. So the answer should be 18B. The sum of square total depends on the variation in the outcome variable. Pearson is different outcome variable, so it has a different SS total. Yeah, that's true. It has a different SS total because that earlier we have a different S, a different Y. Here earlier we have exercise, but the same X. X has been incorporated into the Y calculation, but we're going to focus on the Y, okay? You can remember, I never use X to write the equation. I always write with the head of the Y. You know, remember? I always write with Y. I always wrote everything with the head of Y. See, Y. Y, okay? So the Y is different. That's why that we're going to have a sum of square total outcome. Pearson is a different outcome variable, which is this one. Let's go to 19. Look at the 19, what they're going to do. Now they are compare and contrast, right? Two of them. Pearson pulse 3 group and the exercise pulse 3 group. They are say totals different. And this one. Now let's say what the question was. So, oh no, 19. I will say. Take a look at the two supernova table below. Based on this table, we could argue that pulse 3 explain more of the variation exercise than in Pearson. Explain why would we argue in that space like that? Okay, you can explain that one. Based on these table, we could argue that pulse 3 group explain more of the variation in exercise. See, 636.34 much being explained on exercise than they were doing on Pearson's. So you have to build up the discussion and explain why we would argue that in the space below. See? You explain that one, okay? Right, to explain that one. But 20 again, we could be use the sum of square to argue that pulse 3 group explain more variation in exercise than Pearson. Why or why not? Now we're going to ask about could we use the sum of squares? They mean what? Sum of squares mean what? They are referring to sum of squares means sum of square total. Here they are referring to what? More variation. That means they are referring to what? SSE, SSR, sum of square regression. Okay. Take the look at the two supernova table below. Based on this table, we could argue that explain more of the variation. Pulse 3 group explain more variation means this one. They are referring to SSR. You're going to compare contrast SSR between these two by keeping the same X variable. Okay. Okay. See. 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 So you have to write it down. Can SSR, compare SSR and say, can you do that kind of a comparison? Yes or no? Okay. Can I compare this one with this one? See, that's why they say, they argue. They say, based on this table, we could argue that Pulse 3 explain more of the variation in exercise than in POC. That means they say that we can compare these two. Can we do the comparison between this one and that one? We could, but because the reason that they keep the same, same this guy, okay. But when it comes to this one, look at it. Would we use the sum of squares to argue that Pulse 3 explain more variation in exercise than in POC? We can sum of squares means what? Total sum of squares. Can I use this one and this one, comparing these two, and then argue that this one explain, the Pulse 3 group explain more variation in exercise than in POC? More variation in exercise than in POC. One is exercise model, the other one is POC model. This is exercise, this is for the POC, outcome variable POC. By looking at this, looking at this total. Can you remember it support to that one here? Go back here. Why does this table have a smaller sum of squares total, 1699, compared to the exercise explained by the Pulse in 11,864? The same thing. 1164, this is 1658. Ne? Oh, what happened? Yeah. Yeah. So you have to write, you have to figure, yeah. Yeah. That's right. I'm sorry that I didn't see that one. Then. Yeah, that this is number 19. See, number 19, you have to write it here. Okay. You have to write the answer for this one here. So that's what I'm saying. This is it. We could argue that this one exercise then.
Okay, thank you. Sorry.
Yeah, why we could argue that in the space below. Why we can do like that? If we can do, why we can do that like that? See? To compare what and what? This number and this number. Is it reasonable to compare this number with this number? Can we do that one? They say they could. If we could, if they say you can could that one, why we could argue, why we would argue that in the particular space given below. On the other hand, contrary to that one, here they're going to ask, could we use a sum of squares to argue that Pulse 3 group explain more variation in exercise than in POC? These two compare these two. And they are to support that one. Go back and this one, they say we have two different numbers for those two. Those two numbers say total depends on the variation in the outcome variable. Pearson is different from out variable, so it has a different value. See, you built up that one to get the different numbers. You can get the different numbers, okay, different numbers coming from the sum of square total for reason that they have that different y values, different y. Pearson's and different variables. Pearson and the other one exercise. Exercise versus Pulse 3 group. The other one Pearson's versus Pulse 3 group. Okay, like that. So that one, this number has been different for this reason. So that you have using two different ones. Now they're gonna ask and say, can I use that one to compare? See? Could we use sum of squares to argue that Pulse 3 explain more variation in exercise than the Pearson? Okay. And you have to do very carefully that one. See, here they explain this much. Here they explain this much. You get the different numbers, but that then can you do that one? Which one? Some more variation is explained by that one. Okay, then number. Yeah, let's go to the next one. Okay. Okay, here look at the data set. See? So the following set of question is based on the data called the fat mice. We have seen this one in the earlier slide. See, weight gain for the cage location and all kind of stuff. Data. If you run LM, see, if you run LM to fit the model for weight gain using light as an explanatory model, light is what? Light has two options: normal light and bright light at night. See? Normal light, bright light, LD and LL. So then as explanatory variable, how is error from the model calculated? That's nothing but yes. Yeah, thank you. Yeah, that is a deviation of each mouse weight gain from the mean of the weight gains for each their light group, each group. If you go to each group and then check for their weight gain average for each group and the weight gain of mouse, this is the observed value. This is the estimated value, average for each group. That difference called the sum of squared error or error, simply error. Error would be the difference between y, this is y hat. Okay, that's right. So then number 2, see above is a supernova table of light model which uses light to explain the value. What does it 3.06 here? Again, yeah, thank you. Yeah, 0.60 of the sum of squares from the empty model is explained by the light groups. If you carry that much of error, which is sum of square total, that you see from the empty model is explained by the light. This much of sum of square you carried from the empty model has been explained by the light model. See that model. Okay. The model name is light dot model. Okay. So B. Then again that above. See, above is a supernova table for light. I explain why is the degrees of freedom for model equal to 1. This one equals to 1. 3a. The light model uses upper degree of freedom by estimating one more parameter B1 than the empty model. You see? So that this one is nothing but what? How many regressive variables you have? How many x you have over here? How many x variables? Only one variable. It is nothing but how many degrees of freedom by uses upper degrees of freedom by estimating one more parameter than in empty model. In the empty model, how many parameters you have? If you can look at the same thing in two ways. See, empty model. If you write, you're gonna write the y. I'm gonna write with this one. B naught plus error. See? No x terms. See, empty model equation. If I write the equation. Then the group model equation, you write, you can say y naught, v naught plus v1 x plus v. So here how many parameters you have? One more parameter than here. That's what they say. One more parameter you have than in that one. See, one more parameter than in the empty model. Same as number of x, same thing. One more parameter than in the empty model is 1. You have 1 here. See, here 1 parameter. See, number of parameters. 1 here. Number of parameters 2. So how many more you have in this our group model? 2 minus 1, which is one more parameter than that one, or number of x variables. So that's why 3 is A. Okay. And number 4. And again, we ran this one. Does this result show the light treatment causes mice to eat more? 4. We can remember these are, we can build up only what? We built up only correlation that here we said just a correlation study, no? You see? What do you think? Part number 4. Does this result show the light treatment? Part 4C, yeah, no, we cannot say those are correlation. This study is a correlation of the causation of study. Because the experiment showed that the light causes mice to gain more weight, but does not prove that their weight gain is caused by eating more. So does this result show the light treatment causes mice to eat more? No, because the experiment shows that the light causes mice to gain more weight, but does not prove that their weight gain is caused by the eating more. The light, that's true. They say they show that the light causes mice to gain more weight. That you can see that one, but it doesn't mean that the weight gain means not only due to that eating more. See, so that having that light because of the light they are eating more. See? So this one. Let's say that we calculate the residual from both empty model and the complex model. What is so similar about these two sets of residuals? Same thing, that in both sets of residual represent the what difference between the data and the model's prediction, which is B. No, B. Okay, B. B. Okay, let's go to this one. Then again, above is a supernova table which uses the light to explain variation. What does the table show? Smaller sum of squared error than sum of squared total. Why this smaller? They ask why this smaller. See, what do you think? This is small, this is bigger. That's why they say 182 and I'm sorry, 73. See, this one and this one differ. Why they differ? This is a total, that's the error carried from the empty model. And on the other hand, sum of squared total is based on the residual from the grand mean. Total is based on the grand mean. You know that one. Total, if you're going to calculate, how will you calculate? Y minus Y bar. Grand mean. See, SS error is based on what? Residual leftover after sum of the total variation is explained by the difference in group means. SS error. See, see. 6 is A. 6 is A over. Total should actually be smaller than SS error. This must be an error in the code. Error in the code? No. They ask why this is smaller. This can be smaller for reason. The SS total is based on the residual from the grand mean. SS total. SS error is based on residual leftover after sum of the total variation explained by the model. See? Explained by the difference in group means. See? Group mean. SS total is based on the grand mean. That's true. But the SS error is based on the residual leftover after. This one is after this much being explained by that one. That means you have carried this much. Some being explained by the model because there's leftover. That's why this number is less than that number. That's what they're trying to say. Okay. SS total is based on the residual from the grand mean. That's true. That's true. SS error is based on what? Residual leftover after sum of the total variation is explained by the model. Difference in group means model. Difference in group model is nothing but the model. You know that one. See? You know that one. See? So see that one, see that you can remember that SS total you wrote in a such a way. SS total is always what? See, regardless of that any group, I'm gonna call that on Y and Y minus Y bar. Then here I'm gonna write for all groups, all groups, for all groups. See, based on what? Based on the grand mean, based on the grand mean. See, that one based on the grand mean. Then what? SS this one is what? This one is nothing but you're gonna go to the Y of that group. Let's say that L group, light group minus its own mean squared. Plus that L group, we can say one group is L, the other group is what? So that group is, I'm sorry, this one. What is the other group? I'll say no light. I'm gonna say that no light or something for my convenience. Okay. So this one for light group, this one for no light group or something like that. Y NL minus Y bar. See, NL squared. See. So that's why this is that one. Then error is what? SSC error is what? SST minus SSR. SSCR. So that's why it's low. The error has been that explained. Okay. So the total variation is explained by the difference in group means is nothing but difference in group is nothing but the SSR. Okay. So that's SSR. So that should be B. So that's why this number is smaller. This much been explained. This much is carried from that one. It's larger. Okay, B. And number 9. Number 6, 7. Based on the 2 supernova tables above, we would argue that light top table explain more variation than does cage lock in the cage location bottom. What in the table would support this argument? See, you're going to compare and contrast what? The 2 tables. Light, see, weight gain. See, here what? The Y is the same, okay? Look at the difference here. This is not what we had earlier in exercise and the other one, exercise and can you remember? Or we have that one in the other side that here that we have a different, the Pearsons, I'm sorry, exercise and Pearson being explained by the same. Earlier we had, see here, no? See, here we had earlier that in the previous section we had in the chapter exercise section 1 we have something here and here for what different, same thing, same X but different Y. Now the same Y being explained by different X. Because of the same Y, you can do the comparison. See, I'm trying to explain this by this variable or this variable. See, earlier we had what? Earlier have a different Y's. Different Y's they were trying to explain by the different levels of what is that? I'm gonna go a little bit back to this one and come back, okay? First section we have, just cannot remember here. Exercise being explained by the exercise being explained by pulse 3 group or Pearson explained by the pulse 3 group. Sorry, okay. See that one. Pulse 3 group that we discussed that one. This is the second section. Okay. After that one, we are here. What I'm trying to say Come on, number 7. Number 7 here. Look at here. Earlier, sorry, here we use the pass-3 group here, pass-3 group, pass-3 group. But we here weight the exercise and piercing. Same X, different Y. Okay, careful. But here, same Y, different X. That works because this is the one take into account to that to the calculations. Why? Y would be the same. Then can we do the comparison easily? Yes, we can do the comparison easily. That kind of a comparison, do that one. Can you do this one based on that pre? Can you do this one with the F? Can you do this one with the sum of square model? Yes, all of these we can utilize. Which one has a like a pre? Which one that we're gonna looking into the far better in the pre? Pre is higher in the whatever the model which has a higher pre will be taken into account as the this model. Let's say if this so does with F. Sum of squared, same thing, but when it comes to sum of squared, you can go by the this one. You can compare what this one and this one. Look at here simply. Let's go to the pre. See, weight gain. Simply go to 60%. Here, see, 0.7. 60%, 7%. See, pre. Look at this number. Higher F, lower F. Higher pre, lower pre. See, higher SSR, lower SSR. If you compare these two, see, higher, see, lower SSC, higher SSE. So you know how to compare this to that, that to that, this with this with pre. Higher one would be the same, better pre. Higher one would be the better in terms of F. In terms of sum of square regression, higher one would be the best, better, and lower one would be the better. See, like that. Okay, that kind of comparison built up for with the aid of all these. Okay, so all of the above. Okay, that's one. Okay, then using this one. Okay, using the fat mass data, run LM to fit the model weight gain using light as an explain, blah blah blah. And what is the B note? Yeah, A. Okay, anybody who has done that one, they know that would be A. Find this one, and you go to the number 8. Based on the information supernova table above, how would you calculate the approximate value of pre? Pre. How do you calculate? Everybody knows that one as of now. SSR divided by SST. That's how much? Approximately which one to which one? 2638.1 take out. Okay, they have rounded to the integers. So 9 should be divided by what? 10,485 because they rounded to the next integer. Rounded up, okay? Took the ceiling. This divided by this SSR divided by SST. So answer should be A. Okay. And let's go to the next data set. Next data set, they come back to the same data again. And this time that include the gender to explain the height. Height will be explained by gender. What do you think? Okay, yeah, 10. What are you gonna get? Yeah, if you have run that one, you're gonna get 5.15151. Okay. Gender for which one? Gender. Okay, 11. 11 should be. Okay, let's have a look at it. 11. I explain height with data. What is the mean height of female? Female feet height being given over here 5.151, no? 5.151. If the males and female, make sure that who will be given the male. Who are the male? Gender, student, female and male. Okay, but the who has been taken as the, whose mean is this? 5.155. If this is the mean for that lower one, that you should add the other one, add how much? The gap between those two. So then they're gonna ask that what is the mean height for female? So this is B naught, okay? They say this is B naught, 5.151. Mean height for the female to get the mean height for, how many inches? I'm sorry, that I wanna read this one carefully. Number 10, if I go back to 10, explore the model input gender, explain the height in the student survey. How many inches must be you add to the mean height for females to get the mean height for males? Okay, this is B1. Okay, I'm sorry, B1. This is not B0, B1. B1. Then they're gonna ask you here, female height is the B0. It's the B0. Okay. The male height is they are asking for the male height. Male height should be that much being added to that one. Okay. Fit the gender model. Then use the parameter estimate to calculate the model the prediction for male on the outcome variable piercing. What does the model predict? The mean number of piercing for male. Fit the gender model. Then use the parameter estimate to calculate the model prediction from there. What does the model predict? Model predicts the mean number of piercings for male is what? Mean number of piercings. See? Gender model. Gender to explain. Height has been explained by gender. If you run this one, see fit in gender model, then use the parameter estimate to calculate the model prediction for males on the outcome variable, which is this one. See? It's a prediction is nothing but the mean value. Mean value for the males, if you're trying to estimate the parameter estimate to calculate the model prediction for male, then you use their mean. Okay. A. Using the student survey data frame, run favorite statistics. Simply net part value would use some squared error be lowest. See? At what value would be the sum of squared error be lowest? At what value? It should be definitely at which value? 1.7. If you run that one, favorite stats on siblings. To get what? Let me see. That should be definitely at the mean, no? Sum of squared error becomes 0. The minimize favorite stat on sibling student survey. Okay. I'm gonna get this one. I'm gonna go to student. So that one, see, 1.7. Okay, 13. That's B. Okay. So the last one. That's it. That's the last one. That's the end of the saga. See, that's all. You don't have that much on this one. Okay. I think we pretty much done everything, and then we've done this term, and then I really enjoyed that having you all in this class, and then just finish you all the homework, the assignments, quizzes and everything, midterm, final exam. We're gonna have another more week until we're gonna start the next class, the April 4th. I think we're gonna start the next class. No, yeah, Monday. And for the next class, we keep the same format. Only difference that we're gonna have only one class, one chapter per week. Okay. Do you guys have any questions? Anything that you wanna discuss? Anything?
With regards to the assignments, when is the final cutoff? Do you want the assignments?
I need that one by April 3rd. See?
And then if I'm not familiar, or it's been a while since I've been at NU, but if this class, like the class closes out on Sunday night, which I don't know if it does or not, do you just want us to email you whatever we got? Or you know how we get in this class through Right Learn or whatever it is?
After what, you cannot get into this class after what day?
I don't know. This is my first class.
Oh, no. I don't think that you still can access that one until you're gonna start the next class. No, that's what my understanding, because I'm giving that because officially that will be sent to you, no? Or you can access to that, your grade can be accessed not from this one, access from somewhere else, that where you're gonna from a portal. I think that a student portal, you can go ahead and then get the grade. But this one will be available. But as you said that I exactly don't know what day they're gonna be that be the cutoff date for this our class.
I know in Blackboard, it took at least a week before they closed it out. So you should still be able to access it, even though the class is done.
The class is done after how long? I mean, that's why he was worried about that one. How long is going to be open? Let's say we are finishing class in 26. My understanding, at least it's available at least 1 week before we're going to start this one.
That's what it was in Blackspace or in Blackboard.
Blackspace, no? Yeah.
Exactly. But now I'm not quite positive what this platform offers because I haven't worked in this platform yet, but I think that it's still the same thing as far as staying open at least another week.
Yeah, I think
you're
it
right.
stays,
Yeah,
I
that's
think
my
it might even
understanding.
stay open
They
a
haven't
couple
told
months.
anything about that one to me, that personally, but that my understanding was that they at least they gonna that this gonna that exists for 1 week for you. You can easily access within 1 week. Yeah, but don't worry about that one. If you that when you're gonna turn in everything at the end of the day, that I'm gonna send you all the feedback for all the homework and assignments and everything within that particular week. In that way, that you know that where you are standing at the end of the day. But officially, you're gonna have your grade by accessing that grades on your student portal. I think, if I'm right. That's a different way. Even if let's say that you cannot access this one for certain reason. Okay, make sure that you're gonna get before the let's say 26, you get everything downloaded, like your homework, everything downloaded at least. But this can be that if you cannot, let's say for instance, you cannot upload anything to that system, it's not available. In the worst scenario, you can email me. You email me anything. That's okay. And based on that, I'm going to email back to you that using that our email, and then you pretty much have everything with you. And then by looking at your grades and feedback and everything, you know where you are standing at the end of the but my understanding, I never had an issue with early. I was teaching like a couple of times, that not a couple of times, maybe 4 or 5 times that with the Brightspace, if I'm right. So that student never had an issue because I was giving this grace period all the time, because especially to finish the final exam, because of that. If final is due by next Sunday, I want to be like flexible and give like 1 more week for you guys to finish everything. But during that time, we never had an issue with the student and say, hey, we cannot access. Some student waited last minute and say, oh, I'm going to get this one. Yeah. So I'm going to get this one here, like first go and then try to do the next thing. All of a sudden, nothing is available. That's okay. Still okay, because you can email me. You are in a good shape. Okay. You're not going to miss anything. Don't worry about that one at all. Let's say it's not available at all. But still you are okay. You say, I really need the final exam. Okay, I can send you final exam. Then you work on that and send to me. Any assignment you miss that one. Okay. So you're not going to miss anything at any time. Okay.
Great, thank you.
Yeah. Yeah. Any other questions? Anything? If you have, just email me. I'm going to and then check the email pretty much all the time. So, okay. And I'm grading that you have all that homework and everything too. And all of you did a very great job on assignment so far. So but when I get pretty much everything, I can have a look at it. And then everybody's in a good shape. Okay, don't worry that you roll over to the next class, and then let's continue the same discussion that we had been having over here for a long period of time. Yeah. So I'm gonna let you guys go. You guys have a good night. Have a nice weekend, and then see you in like a week. Okay.
Okay,
Good night.
Thank
Sounds
you
good.
very much.
Have a
Bye.
good
night.
weekend.
Thank you.
Bye.
Thank you. Stay safe and be well. Okay. Take care.
You too. Yeah.
Thank you. Thank you very much. Thank you.